Okay, hi everyone. It's Miss Yam, and I'm not in school for our first period today because I had a commitment elsewhere. But Mrs. Ament was kind enough to step in and hold up some visuals when I cue her. So thank you, Mrs. Ament. I know I appreciate you, and I'm sure they do as well. Today we're going to talk about the SSA acute ambiguous case. This is the very last day of solving triangles, and I think the SSA acute ambiguous case is probably the most involved one. First, a recall before we move forward. We know that if we're asked to solve a triangle, and if we are given SAS or SSS, we start with the law of cosines first, and then we can transition over to the law of sines. If we're given AAS or ASA, we can use law of sines all the way through to solve a triangle. I think we are all in general agreement that the law of sines is easier than the law of cosines, just in terms of algorithmically. It's less messy, it's shorter, it's smaller, it's cleaner. We talked about the SSA obtuse case. And let's just recall that in the SSA obtuse case, the SSA is specifically a result of being given an angle, being given a side opposite the angle, and then being given a side adjacent to that angle. Let me say that again. SSA is the result of being given a triangle's angle, a side opposite the given angle, and a side adjacent to that angle. And what we talked about successfully last week was the fact that if we're given an SSA obtuse case, we know there is one triangle to solve if and only if the opposite side, the side opposite the given angle, is greater than the adjacent side. And over here, I don't know exactly what happened to this drawing here. But, for example, here, if we were told to solve a triangle where you have an angle, 110 degrees, 7 inches, and let's call this 4 inches. Okay, let's say you're asked to solve this triangle. Well, there's a couple of things that I hope you recognize. This is actually a question that I often see. A triangle is just drawn and you're asked to solve it. Just because a triangle is drawn does not mean it's possible. Some of you will recognize that if this angle is obtuse, 110 degrees, and that means the two other angles of the triangle have to be acute. And if you have a triangle where the largest angle is not opposite the largest side, you know that's an impossible triangle to solve. That a triangle cannot exist in that fashion. There's a direct relationship between the size of the angle and the relative size of the opposite side. So here, the fact that 4 is less than 7, yet 4 is opposite an angle that is larger than the angle opposite 7 makes this triangle impossible to solve. I think what I asked you to do was to recognize when you're asked to solve an SSA triangle given condition, to redraw it with some degree of accuracy. And if I do that here, look what happens. It becomes a little bit more visually obvious. If that angle is obtuse, if this length is 7, let's draw a length of 4 with relative accuracy. Well, if this length is 7, then 4 is about here, okay? And you'll see that this angle is, not fixed. The 110 is. And as this 4-inch side tries to swing around and connect with this length to create a triangle, it is too short. Okay, and we talked about the fact that if this side opposite, even if it equaled 7, right? If it equaled 7, it would swing around and intersect right here at this vertex, still not creating a triangle. So in the SSA obtuse case, the only possible triangle that you can solve is one where the side opposite the given angle is longer than the side adjacent. All right, so that was just wrapping up there. Okay, so here's where we left off with, what did I do here? Oh, I see. I was setting this up this way. Let's say, maybe you were given a question like this one. Solve triangle ABC where measure of angle B is 140, C is 7, and B is 5 inches. Okay, and let's say you didn't recognize it was SSA, and let's say that you just drew a triangle, and you immediately launched into just trying to solve this triangle. Okay, and here's my work over here. So you set up this drawing here. You didn't recognize that this triangle is impossible to even exist, but you said to yourself, I'm just going to jump right in, use law of sines. Sine 140 over 5 right here equals sine c over 7 right here. And then you solve for sine c. And if you're doing this with me, and maybe you're pausing if you need to, if you're doing this here, you'll find that this angle, like sine c equals this number is going to not be between -1 and 1. And how do I know that? Well, because the sine of an angle is always a value between -1 and +1, -1 and +1, right? It is impossible for the sine of an angle to be outside of that range of numbers. If you think about the graph of y equals sine theta. So you will have some number here that is definitely outside that range. And let's say you still didn't pick that up and you went into your calculator and did inverse sine of that number. Okay, you will get an error reading. Okay, you'll get an error as your output. That's when you know that the situation, that condition that you were solving was impossible. Okay, so on to the SSA acute case. So let's come down here and take a look at this. The SSA acute case, I'm asking you here, let's solve triangle ABC where the measure of angle A is 40, A equals 5, and C equals 6. And once again, if you look at the SSA, you're given an angle, you're given a side opposite the angle, and then you're given an additional side. That is the SSA case. I'm going to go down here and draw this triangle with relative accuracy. Nothing perfect, but just something to give us some sense of just a visual. All right, this is the known angle A. The side opposite it is 5. The side adjacent here is 6 inches. Okay, I'm going to be reasonably accurate. So this here is 5. Okay. Now notice something. This is the SSA acute. If this were the SSA obtuse and the side opposite is less than the side adjacent, we would already know that is impossible. The question here is it obvious to you, is it visually clear to you when you look at this picture that, 5 is not going to intersect this base to create a triangle? And I think we agreed last week that the answer was no. Like some of you said, I forgot who it was, someone said, this angle could be acute enough, right? It could be small enough such that the side opposite, even if it's less than the side adjacent, could be, could create a triangle. Someone else said that, I don't remember what it was. I think someone said, well, if you look at this segment 5, if it's swinging around here, will it make, will it be longer or shorter than this length here? Okay, well, let's talk about that length. That length is, I just did a perpendicular drop, all right? So this vertex, that point of the triangle, this dotted distance here is the shortest distance from this vertex to this line. So back in geometry, or at Shadyside, it's probably Math 1 and Math 2, right? If you're asked to find the shortest distance between a point and a line, that distance is always the perpendicular distance. Okay? The shortest distance between a point and a line is the perpendicular distance from the point to that line. So the shortest distance from this point to this line is this perpendicular drop. I will call it H. So here's my question to you. H is the shortest distance from this vertex to the base. Okay, that's the shortest distance. If H ends up being bigger than 5, one more time, if H is a number that's bigger than 5, as this 5 swings around, will this segment hit this base? Miss Ament, can you hold up that little ruler thing right there? One more time. If this distance, which is the shortest distance from the point to this base, if this distance is longer than 5, will this 5-inch arm ever hit the base? The answer is no. So let's write this down. If H is bigger than the opposite side, no triangle is possible. Okay? That's probably the most obvious thing to see. Okay? If h is greater than the opposite side, no triangle is possible. So I guess the question is, let's find h. So if you're finding h, here's what I want to do here. I'm going to highlight something. I'm going to go down here and highlight this right triangle. Okay, now remember, just to be very clear, this right triangle here is not the triangle that I'm solving for. That's just the right triangle that I'm going to use. It's going to allow me to find h. Now what I'd like you to do is to think about how on earth you would find h. This yellow triangle, there's an angle of 40, there's 6 inches, and there's this length h. How would you find that length h? And I think many of you are seeing that I could use sine of 40 degrees equals h over 6, since this is a right triangle. Okay? H equals 6 times the sine of 40 degrees. Okay, and this h length is 3.86, right? All right, so now what I'm going to do is, and Miss Ament, maybe you could go ahead and fix your ruler so that we have, you know, an angle of 40, of 6, this is 3.86, and this is 5. Because what you're going to see here, and maybe Miss Ament will do it with me right now as we do it in tandem, and we're going to do this. Okay, here is A, here we go. All right, so this length is 3.86, right? This length is 5. Okay, everyone watch Miss Ament as she goes and swings this arm around. Look what happens. When this 5-inch, 5, by the way, this opposite side is bigger than the height, and notice something, it's less than the side adjacent, it hits once here, and it hits once here. Okay, and what happens, so here is case 2, if, all right, if h is, it's two things, right? Less than the opposite side. I need more room. Okay, if, actually let's write it this way, if the opposite side is bigger than h, but also less than 6, right? If that opposite side is between h and the adjacent side, you have two possible triangles to solve. And yes, when there are two possible triangles, you have to solve them both. So what we've got here are two conclusions to the SSA acute case. One, which is the most obvious one, if h is bigger than the opposite side, there's no triangle. If h is less than the opposite side, which is less than the adjacent side, you have two possible triangles to solve. What I'm going to do down here is kind of highlight one triangle looks like that. Here it is. Okay, this is 40 degrees, this is 6, this is 5 inches. This is A. Did I call that C? Oh, yeah, yes, very good. This is vertex A, vertex C, vertex B. But here's the second triangle that's possible. Here to here to here. And again, look at Miss Ament as she kind of swings that ruler back and forth. Right? Here's that one. And it looks like this. This is 40 degrees. This is 5 inches. This is 6 inches. Vertex A, vertex B, vertex C. Okay? Now, I also want to ask you this question here. Look at the pink triangle. I'm going to come down here and do this. Look at the pink triangle. Look at this angle, which is right here. I know it's getting a little bit crowded. And look at this angle right here, which is this one. Okay? Tell me what the relationship between this angle C and this angle C is. They are supplementary. The two angles C are supplementary. Okay, which means the two angles C add up to 180 degrees. And I know there's going to be triangles upon triangles here, but if you want to see why, this 5 inch is a swinging arm, right? That means this length here is 5 inches, this length here is 5 inches, this triangle it's dotted is actually isosceles. If this triangle is isosceles, that means this angle equals this angle. And if you look here, this angle plus this angle is 180. All right? Okay, now Ms. Ament is going to talk you through solving this. All right? If you look at this, I'm going to use the law of sines and take out your calculators, and although they're probably out, and I'm going to do this. Sine of C over 6 equals the sine of 40 degrees all over 5. Go ahead and solve for angle C. The measure of angle C equals what? I want someone to answer this question. Why is it when you use your calculator, why is this angle acute? Why must it be acute? Okay, what domain of invertibility, perhaps, is your calculator obeying? In other words, when you do this, you find angle C. Why is this angle acute? Why wouldn't your calculator ever give you, say, the measure of this angle? Because if you look over here, if I want to solve for this angle C, one could argue, well, I would still do here sine of C over 6 equals sine of 40 degrees over 5. And you're probably wondering, how on earth could these two proportions that are identical yield two different angles C? Well, I'm going to ask you to think about something, and here's a hint. Remember that for sine, the sine of an angle is positive in quadrant 1 and in quadrant 2. When you find this angle, and I want you to kind of talk amongst yourself with Miss Ament there. Why is this angle? Why do I know for a fact this angle is going to be acute? How do you then figure out the measure of the other angle C? Okay, and then once you find angle C in both these triangles, how do you go about finding angle B here? Right? That should be fairly straightforward. And then, of course, you have to go ahead and solve for the missing side B. Please go ahead and do that and pause me here as you kind of do this and answer questions along the way. And then I'm going to start with another condition. Okay? Okay, now we're going to go here and do this. Let's say we have the same triangle. Let me set it up. Okay, you'll see here, this is also an SSA, solve triangle ABC, where you have a given angle, the side opposite, and the side adjacent. But in this case, the side opposite is greater than the side adjacent. It is bigger than the side adjacent. Well, let's see what happens. And maybe you can probably, some of you already see this already, what's going to happen, and maybe some of you don't. And Miss Ament is probably holding up the little ruler right now. But let's say this is angle A. The side opposite is 5. The side adjacent, excuse me, I just said it backwards. The side adjacent is 5. The side opposite is 7 inches. Okay? Is it obvious to you that in a case where you have an SSA acute, if the side opposite is bigger than the side adjacent, and Miss Ament is probably holding up her rectangle, or her ruler, that this will always create a triangle. As this swings around, it will just come down and hit once, right here. Okay? It'll hit once. But because 7 is longer than 5, if this 7-inch arm keeps swinging around, it's going to come around and then like intersect again, but past this vertex A. Okay? So condition number 3 in the SSA is if the side opposite, okay, if the side opposite is greater than the side adjacent, you have one triangle to solve. So then I'm going to look back here and recognize, I've got this situation for SSA acute, side opposite bigger than side adjacent. I have the case where the opposite side is between the side adjacent and the height, and I have the case where the height is bigger than the opposite side. Do you think I'm missing anything? Do you think I'm missing any possibilities? Let's say maybe, is there a possible way for the opposite side to be bigger than the height and also bigger than the adjacent side, right? I'm going to ask that question again. See how I said here, the opposite side is bigger than the height and also less than the adjacent side. What if I told you you have a case where the opposite side is greater than the height and also greater than the adjacent side? Well, I hope you recognize that that is nothing different than this case right here. Okay, so what we've done here, everyone, is kind of fleshed out the SSA acute ambiguous case, and hopefully you see why the SSA acute case is kind of a potentially pain in the, well, I guess it's a pain in the ASS to a certain degree, right? You have to kind of think about all these possibilities. But once again, I kind of stand by my belief that redrawing an SSA acute case this way helps to visualize the possible scenarios. Miss Ament, thank you for your help today. And I'm going to ask that she assign some homework from the textbook on solving triangles that involve the SSA ambiguous case, both obtuse and acute. The other thing, boys and girls, you do have your last and final assessment tomorrow. It is a quiz, and for quizzes we don't have question day. But the quiz tomorrow is your last assessment, and let me tell you what could be on that quiz on Tuesday. Okay, here is what is fair game. Solving a trig equation. Okay, solving a trigonometric equation, and I would ask that you look at the handout that we used where we substituted in u, sometimes u and v, and some of you skipped that substitution step. You're going to be asked to solve a triangle or two. What I cannot include is this SSA acute ambiguous case, but I absolutely can include the SSA obtuse case. And then what I'm going to do is I'm going to ask a few questions that involve inverse sine, inverse cosine, inverse tangent. So I would like you to know the kind of the ranges of invertibility for inverse sine, inverse cosine, inverse tangent, because you could be asked questions like this. The inverse tangent of negative root 3. I should say of these three topics, this one was included on your last test. All right, thank you, and I will see you on Tuesday, and thank you, Miss Ament, for assigning homework for this class.